Welcome to the Chemistry, Biology and Math Revision Hub. Today we're doing the Pearson Edexcel International A-Level Chemistry Unit 6 for January 2022. This is the unused paper, so let's begin with question 1. Question 1 says, compound X is a green crystalline solid that contains 2 cations, 1 anion and water of crystallization. Tests were carried out on X. State what we can deduce about X from its color. So I said X is a transition metal, which could be iron 2 or chromium 3. In part B, about 2 centimeters cubed of aqueous sodium hydroxide was added to a few crystals of X in a test tube, and the mixture was warmed gently. A pungent gas was evolved that turned damp red litmus paper blue. Identify by name or formula the cation that is indicated by this test. Because they said a pungent gas, and the gas that turned damp red litmus paper blue, that should be ammonia gas, and therefore the cation should be ammonium. In part C, a spatula measure of X was dissolved in about 20 centimeters cubed of distilled water to form a green solution Y. Portions of Y were tested. They want you to complete the table. So when 1 centimeters cubed of aqueous barium chloride was added to 5 centimeters cubed of Y, and the inference here is, as well as the sulfate ion, 2 of the anions that might give the same observation. So if this was sulfate, the observation should be a white precipitate. And then here we're looking for any 2 other anions that could give the same. One is a carbonate, and the other could be that, or it could be this one here. And again, this is 2 minus. So moving down here, 5 centimeters cubed of dilute hydrochloric acid was added to the reaction mixture. And then they say sulfate ion is present. A sulfate will be already formed, so there will be no observable change. Moving on. So here they say a few drops of sodium hydroxide solution were added to 5 centimeters cubed of a fresh sample, and a green precipitate formed that remained unchanged on standing. This is very important. So that means if it didn't change on standing, therefore it should not be iron 2, because iron 2 would have been oxidized to iron 3 and the color could have changed. So a cation responsible for the green color should only be chromium 3. And moving down here they say sodium hydroxide solution was added to the mixture from C3 a little at a time until there was no further change. The green precipitate dissolved to form a green solution. Complexes of chromium 3 dissolve from green precipitate to a green solution when excess sodium hydroxide is added. And they say the formula of the ion responsible for the green color of this solution should be, this is it. This is going to be the formula of the complex, or the formula of the ion. The next they say hydrogen peroxide solution was added to a green solution formed above, and the mixture was warmed. Now, every time they add hydrogen peroxide, think of it as a good oxidizing agent, and therefore chromium 3 is being converted into chromate 6. So the green solution, of course, turned yellow, and this is showing you that that is chromate 6, which is that. So they ask the ion responsible for the yellow color of the solution. This is going to be that, which is chromate 6. The next part is very predictable. Once you see this, the next step is going to be addition of an acid. So they say dilute sulfuric acid was added to the yellow solution, and yellow solution turned orange. The ion responsible for the orange color, of course, it's going to be dichromate ion, which is that. So down here they say, state what can be deduced from the observation in C3 that the green precipitate does not change on standing, and justify your answer. If the green precipitate did not change on standing, it means the cation present couldn't be iron 2. So I say that it cannot be iron 2 because if it was iron 2, oxidation could have occurred. So I said because if it was that, meaning after adding a few drops of sodium hydroxide, you would form this. This cannot be the precipitate since it would have turned brown or red brown on standing, because it could have been oxidized to Fe or H3H2O3, which is going to be the complex of iron 3. Give the possible formula of X. Water of crystallization is not required. Now we know X contains ammonium, it contains sulfate, and it contains chromium. Because chromium is 3 plus and ammonium is 1 plus, it means the cations have an overall positive charge of 4. So the anion, because it's sulfate, they have to be 2 of them in order to form the compound. And again, to explain this again, these have a total of plus 4. These ones here, they have a total of plus 4. The anion should have a total of minus 4 in order for this compound to be formed. So that is why I put 2 on the sulfate. So it could be represented like that, or you could say Cr2 NH42 and that or that. All of them are acceptable as the answer. So this brings us to the end of question 1. Let's continue to question 2. Question 2 says compound P is a white crystalline solid and the percentage composition by mass of P is carbon 60.87, hydrogen 4.35, and oxygen 34.78. They say the mass spectrum of P has a molecular ion peak at mass to charge 138. They want you to determine the molecular formula of P using all this data, and you must show you're working. So the elements present here are carbon, hydrogen, and oxygen. I put their percentage compositions by mass, which is 60.87, that which is that, and that which is here. Then atomic mass of carbon is 12, that is 1, and this is 16. Then to find the number of moles, divide that by that, which I got here, divide that by that, which I got here, and divide that by that, which I got here. Now the next part is for me to find the mole ratio. The ratio came out to be 7 to 6 to 3. And this means the empirical formula is carbon 7, hydrogen 6, and oxygen 3. So that into N equals 138. 12 times 7 plus 1 times 6 plus 16 times 3 into N gives me 138. I got N is equal to 1. And therefore, the molecular formula and the empirical formula are exactly the same. So this is our molecular formula. Carbon 7, hydrogen 6, and oxygen 3. Moving on. In part B, samples of P are subjected to a series of tests. When a spatula measure of P is added to a solution of sodium hydrogen carbonate, vigorous effervescence occurs. If vigorous effervescence occurs, when sodium hydrogen carbonate is added, this organic compound is a carboxylic acid or it contains a carboxylic group. And then, when a spatula measure P is added to cold solution of acidified potassium magnate 7, the color of the solution does not change. That means it does not have a carbon-carbon double bond because the color would have changed from purple to colorless. The next they say, when a spatula measure P is added to a dilute solution of bromine water, the solution turns color and a white precipitate forms. When phenols react with bromine water, the color changes to colorless and then a white precipitate forms. So this shows us that P has a phenol group. And then next they say, when a small sample of P is ignited, it burns with a smoky flame, so we can see highly unsaturated, so that could be aromatic. They say state what could be deduced about P from all these tests and justify. So here I said, effervescence with sodium hydrogen carbonate confirms presence of a carboxylic group. No reaction with cold solution of potassium magnate 7 confirms absence of a carbon-carbon double bond in alkene. And then reaction decolorizing bromine water accompanied by the formation of a white precipitate confirms a phenol group. Then burning with a smoky flame confirms presence of an aryl group because it's highly unsaturated. So moving on. Here they say, describe how you would ignite of solid P to show that it burns with a smoky flame. You may include a label diagram in your answer. Now I did something like this. You place the sample in a crucible and then you put it on a specific stand. It could be a tripod stand and in a crucible, and then you will ignite it from above using a Bunsen burner. The use of a tripod stand is to ensure that the place where you're burning from is stable. So a description of something like this would be okay. So I said, place the sample on or in a crucible or evaporating benzene, on a tripod stand or pipe clay triangle. Ignite the organic substance P from above the crucible using a Bunsen burner. Moving on. Use the information from A and B to draw 3 possible structures of compound P. Now remember, if we go back here, we got it was carbon 7, hydrogen 6, oxygen 3. We know it also has a phenol group. So it has a phenol group like that. That is already 6 carbons. It means there is going to be a 7th carbon. That is going to be a carboxylic acid. So we can see there is a possibility of that. This could be on carbon 1, or it can be on carbon 3, or it can be on carbon 4. So we can have a 1,2, a 1,3, and a 1,4. Moving on. So here they say, the infrared spectrum of P is shown. One of the peaks has been circled. So we have that here. We have the transmittance on the vertical and wave numbers on the horizontal. So let's go to the real questions. They say the infrared data for some organic functional groups is also given here. And then down here they say, explain how the Sakharov peak in the IR spectrum and the table of infrared data may be used to deduce the structure of P. If we go back here, the peak is at about 750. So that is 750. And when we come back here, 750 corresponds, which is here, corresponds to an arene with 4 adjacent hydrogen atoms. 4 adjacent hydrogen atoms, if we go back to our possible structures, here we have a hydrogen, a hydrogen, a hydrogen, and hydrogen. So 4 hydrogens are adjacent. Here we have 1, 2, 3. There is no hydrogen here and there is no hydrogen here, so that is out. For here we have adjacent 1, 2, because here and here we have no hydrogen, and here 1, 2, so that is wrong. The only possible structure is going to be this, because we will have 4 hydrogens adjacent to each other. So that means the possible structure could be this. So I said the wave number of the Sakharov peak is 750 per centimeter. It has 4 adjacent hydrogen atoms, and this structure is only possible if OH and COOH are on adjacent carbons. So this brings us to the end of question 2. Let's continue to question 3. Question 3. Iron 2 ethandioate is an orange solid which is only slightly soluble in water but dissolves in dilute acid on heating. The formula of the compound is given as that, where X is the number of moles of water of crystallization. They say the number of moles of water of crystallization in that compound may be determined by titration, and the procedure is as below. So accurately weigh approximately 2 grams of iron 2 ethandioate into a 250 centimeters cubed beaker, and then add about 100 centimeters cubed of dilute sulfuric acid to the beaker and heat the mixture until the solid dissolves completely. Then use the solution prepared in step 2 to prepare 250 centimeters cubed of iron 2 ethandioate solution. Then fill a burette with a standard solution of potassium manganate 7, and then transfer 25 centimeters cubed portion of the iron 2 ethandioate solution to a conical flask and heat it to about 60 degrees Celsius. Then titrate the hot solution with the potassium manganate 7 solution. In step 6, repeat step 5 until concordant results are obtained. So they've given us the half equations for the reactions in the titration, which is that, and that. So they told us describe the procedure in step 3. And again, to take you back here, use a solution prepared in step 2, which was 100 centimeters cubed of dilute sulfuric acid in a beaker and heated to prepare 250. So you have 100. You have to transfer this 100 along with its washings into a 250 centimeters cubed volumetric flask to fill up and then shake in order to create a solution of uniform concentration. So I said transfer the 100 centimeters cubed solution into a 250 centimeters cubed volumetric flask, and then add some dilute acid to the beaker and transfer the washings. Then make up the solution to the 250 centimeter cubed mark with dilute sulfuric acid and mix in order to create a uniform solution. So moving on. They say state the color of the solution at the end of the titration. It is going to be pale pink because this is manganate that is being titrated with, and as you put in manganate, the last drop is going to turn it to pale pink, from colorless to pale pink. In an experiment, 2.02 grams of iron 2 ethandioate was used to prepare the solution, and potassium manganate solution of concentration 0.0195 mole per decimeter cubed was used in the titration. The mean titer was 34.25. They want you to calculate the value of X in this compound, giving your answer to appropriate number of significant figures. Based on this formula, 1 mole of this is going to produce 1 mole of iron and 1 mole of ethandioate. And again, this is iron 2. But iron 2 from this compound is going to be reacted like that. Also, this is going to be converted in this manner. And again, this has 2 things that are reacting. You can see we have that reaction and that reaction. These 2 are included in the compound we have. A total of 3 electrons are going to be produced. So these electrons are going to participate in the reaction with manganate. So this means if I bring this down here, that is going to become that, and that, combining these 2, meaning this becoming that and that, which is what we see here. 2 carbon dioxide, 3 electrons, and 1 Fe3+. Now this is what is reacting with this in total. Here we see 5 electrons, here we see 3. How can we make them uniform? Multiply this by 5 and multiply that by 3 in order to create the overall equation. So after multiplication, I got 5 of that equals to 5 of that, 10 of that, and then 15 of that. Here we have 3 of that. That is going to be 24. That is going to be 15. That is going to be 3. And that is going to be 12. So we have 2 grams of this. And then we have, basically, this is going to give us the general equation as the electrons cancel out. So even if I don't write the overall equation, this is okay. So we have 2.02 grams of that. And the information for this concentration and volume is given from the information in the question. So since I have this, I began by finding the number of moles of manganate. So the moles are going to be concentration times volume, which is that, times that divided by 1000, and I got these moles. Now, to find the number of moles of iron, you can see the ratio is 3 to 5. So it's going to be, finding moles of that, it's going to be 5 over 3 times the moles of manganate, which are these. So 5 over 3 times that, give me that. Those are number of moles in 25 centimeters cubed. So to find the number of moles of that in 250, I have to multiply that by 10, which gave me this. Now these are the moles in the 250. Since I have the moles and I have the mass, I can be able to find the MR, which is going to be mass over number of moles. And I got 2.02 divided by the number of moles I got here. And this gave me the molar mass, which is 181.471 gram per mole. Now, since I know this is my compound, I can subtract away this. My aim is to find the value of x. And in the end, I got x is equal to 2.09. Please do not round off this because you can see if you round off, it's going to be 2.1, which is wrong. X should be a whole number. So x is approximately 2, and that is my answer. So let's continue on. Here they say another experiment followed the reaction of ethandioate ions with manganate 7 ions in acid, and the results are shown. So here we have the graph. And again, ignore I use some of this part for my calculations for the questions that are coming up. So when we move on here, they say, describe in outline a continuous monitoring method for obtaining results such as these. Practical details are not required, but any essential apparatus should be named, and the means of obtaining concentrations from the measurement should be stated. So you could use any methods like colorimetry, spectrometry, transmittance, absorbance, but I chose using a gas syringe to collect. So I said using a gas syringe, you collect the volume of carbon dioxide gas produced. Using the molar volume equation, you will convert the volume of gas to moles, and then the moles of manganate can be obtained, and then the mole ratio can be used to obtain moles of the compound, which is this, and then the MR can be obtained. Or you could measure change in mass. Because a gas is coming off, you could measure the change in mass over time by carrying out the experiment on a balance, and then you could use the number of moles is mass over molar mass equation to convert the mass of CO2 lost into moles of carbon dioxide generated, and then finally into moles of the manganate. So next they say determine the rate of reaction at point A and at point B. You must show you're working on the graph and include units with your answer. So going back here at A, I drew a tangent at that point, and then the points I use for calculating the rate are that point as well as that point. Then my rate was 3.4 minus that divided by that minus that, which gave me about 9.38 times 10 power negative 7 mole per decimeter cube per second. And then at point B, this was already a straight line, so I just used specific points. I chose that as well as that. So calculating, I get a rate of 5.56 times 10 power negative 6 mole per decimeter cube per second. So these were my two answers I put here. And then here they say, explain why the values obtained in B2 are different from the results of the typical rate experiment. In a typical rate experiment, of course, the initial rate is the fastest. However, here, the rate of reaction at point A is slower than at point B. And again, if you remember, this is an autocatalyzed reaction. The initial rate is not the fastest, but the rate increases with time as more manganese 2 is produced, which catalyzes the reaction. So I said, in a typical experiment, the initial rate is the fastest. However, here the rate of reaction at A is lower than at B, and this is an autocatalyzed reaction. The product, which is Mn2+, catalyzes the reaction, so the rate speeds up as the reaction progresses. So this brings us to the end of question 3. Let's continue to question 4. Question 4. The identity and purity of an organic compound may be checked by measuring its melting temperature. students were asked to determine the melting temperature of samples of a solid organic compound using the apparatus shown. We have the fuel tube, thermometer, capillary tube, Bunsen burner. We have the beaker containing a clear mineral oil, rubber band, as well as a solid sample on a watch glass. This is melting point determination. So here they say, if the steps of the procedure to determine the melting temperature of the solid organic compound using the apparatus shown, you may include a diagram in your answer. You do not need to show how the apparatus is clamped in position. Yeah, we didn't need to show this, but I showed it anyway so that it's easier because this is a teachable moment. So I said, using a Bunsen burner, you heat and seal the capillary tube, and then you transfer the solid into the cold tube. The capillary tube is that. Actually, initially it has both ends open. So you heat one of the ends on a Bunsen burner so that it softens, and then you seal it. When it cools down, then you put the sample inside. So you have to tap gently for the solid to be directed at the bottom of the capillary tube. And then you fill the fuel tube to just higher than the upper arm with clear mineral oil. It has to be clear so that you can be able to see when the sample melts. Then using a rubber band, attach the capillary tube to the thermometer, ensuring that the bottom of the tube is near the thermometer bulb, and then insert them into the fuel tube. The position of the sample at the bottom and the bulb of the thermometer should be at the same position or should be tied at the same point so that they are close to each other. Then heat the fuel tube on the side arm with a Bunsen burner like you're heating here, and then note the temperature when the solid just changes to liquid. That will be your melting point. And lastly, here they say, state how the melting temperature of an impure solid of an organic compound would differ from that of a pure compound. Simple, the melting temperature of the impure solid would be lower, or you would say it is going to melt gradually over a range of temperatures, while the pure sample will have a sharp melting point. So this brings us to the end of question 4, as well as to the end of this paper. Thank you for being with us. Do not forget to subscribe. See you in the next video. Bye-bye.